Do you like chickens? Do you like dots? Do you like crosses? Do you like math? Do you like art? If you've answered yes to any of these questions, you're gonna love this video.
Well, that was a weird intro. Hi there, everybody. I wanted to make hopefully a short video. We'll see how long this ends up being about two mathematical concepts in 3D art, that being the dot product and the cross product. I teach at East Stroudsburg University, and I find art students are sometimes a bit fearful of math in art, so I wanted to make this video series demystifying some of these concepts and showing some practical uses for them. So let's get into it here in Houdini, although this would apply to any software. So I'm gonna turn off my webcam for now. And let's look at a few things. So before we jump into this thumbnail art, let's get some basic concepts covered here. One thing that both dot products and cross products deal with are vectors. And vectors, at the base definition in my mind, it is just 3 floats. So a vector is 3 floats, and a float is just a number that can have a decimal, right? So 1, 2, 2.5, 3, all those are floats. And so a vector is a set of 3. This can be used for many things. So if we think about 3D, all the positions on your 3D coordinate system are represented by a vector. So you have your X, Y, and Z translation here. So if I have a point, I can move that point up 1 unit, and now this point's position is at 0, 1, 0, and that's the vector. And so this vector actually indicates both a direction and an amplitude. So in this case, or magnitude, I might get some specific math terminology wrong, but really the base concepts here are what's important for us 3D artists. So you can see here that we've moved from the origin 0, 0, 0 up 1 unit in a direction. So we have a magnitude of 1 and also a directionality. We could have moved this point over, if I go back to this transform, 1 unit on the x-axis, and now we would be moving in that x direction. So we have a vector. That's a vector. The other thing to realize about vectors is what we call normalization. So if I were to move more than 1 unit, so if I were to, let's say, move up 2 units here on the transform, or even less than 2 units, it doesn't really matter. What happens when you normalize a vector is it changes the length of that vector to 1. It normalizes it to a unit of 1. So if I have this little code snippet here that normalizes the position, and I preview that, no matter where I put this dot, so if I start moving this dot around, you can see it always will stick to a unit circle. So it will never have a magnitude greater than 1. And that is what normalization means. And that is why the normals of geometry, so if you've done 3D graphics at all, you know a normal is that perpendicular vector to the surface of your geometry. That has a unit length of 1. And that's where that name comes from. A quick little fun thing is if you normalize the position of all the points in any object, it's going to make a sphere. So we can see I took this pig head, I ran the same script, so it's taking the P at P as position, and it's just normalizing that position, and it makes all of those points a unit sphere. So that's what normalization is. It's helpful to keep all your vectors normalized when dealing with some of these operations. So that's a vector. three floats. And so what's interesting about vectors is it doesn't just have to be like positions in space. So a vector can be anything, and we can see colors are vectors. We can see our view axis down here in the corner, and we have these three arrows. These colors represent these vectors or positions in space. So we can see on Z is blue because we're moving 0, 1 in space. Then we have X and Y, and these RGB values of 0, 1, 0, 1, 0, 0, and 0, 0, 1, that red, green, blue, represent those directions. So if we take something like a sphere and we put points in it and we have those points represented by their colors, we get this sort of color wheel, right? And so this is just kind of a tangent. So we realize that all it is it's three values. So those three values can represent a lot of things, and a lot of things can represent those values. So here we have colors representing those values. If we expand the sphere or make it smaller, those colors get dimmer, right? So as we get higher values, those colors get brighter and brighter and brighter and brighter and brighter. And then if we made a smaller sphere, but we normalize the color, which you could do, they go up to maximum value. So a normalized color just is at the maximum value in saturation there. So that's pretty interesting, normalizing a color. You wouldn't really think about that normally. All right, so let's get into dot product to start off with. So dot product is pretty useful for several things, but let's sort of explain what dot product is to start off with in basic terms. What a dot product does is it tells you if two vectors or directions are facing the same way. So the way this works is you can compare two vectors, any two vectors, which are three floats, right? And if they face the same direction, that dot product equation is going to return the value of 1. If they face opposite directions, it's going to return a value of -1. And if they're perpendicular, it's going to return a value of 0. So let's look at a little visualization of this. I have set up this little node system in Houdini where I create a point and I am creating a normal direction. So this normal direction is simply pointing towards this other point. So I have 2 points in space, and one point is always pointing towards the other, the normal. Now what I could do is use the dot product to check if that normal direction is aligned with any other vector. So in this case, I have this little snippet of code here, and I'm using a reference vector of 0, 1, 0, and I'm using this dot function here to check if my normal of my point matches my reference vector. So now what we can see happening is if I move this point, and I've used this little color visualization, if it is bright green, it is perfectly aligned and the dot product is returning a value of 1. If it is red, they're perfectly opposite facing and it's returning a value of -1, making it red. So I'm checking now if this arrow is facing 0, 1, 0 or straight up, and it is. If I start moving this arrow, as we start facing downward or perpendicularly, it changes to this yellowish orangish color, which is right in the middle, or 0. And then if I keep on moving this downward and it faces straight down, it changes completely red, which means it is returning a value of -1 or red. So really, just to put it again simply, the dot product is just a tool that lets us check if one vector is aligned with another vector. So let's expand upon this and see some practical applications. Here we have the same dot check just applied to a sphere. So we have the same bit of code where we're taking the reference point, the position of a reference point, and we are just seeing if the normals of the sphere, so just to show you the normals, they're just facing straight out, just like any other normal. We are checking to see if they are aligned to that vector in space. So let's use the same color visualization. Green is aligned, or it's pointing towards it. Red is it's pointing in the opposite direction. And you can see if I move this point here, which is straight above the sphere, if I start moving it over, this whole gradient starts to shift. So that's interesting. And I think at this point, maybe you can start seeing some creative applications for this math, this dot product. So let's take a look at kind of an real world application of this. Not real world, but CG world, I guess. One thing that it comes in handy for is doing any sort of shading where you need to check if certain faces or primitives are aligned in a certain direction. So here I made this kind of rocky column. I just made a tube, subdivided it a lot, and added some noise. So we get this very kind of intricate geometry here. Let me turn on the lights again. So we have this very rocky sort of column. We can use dot product to determine what faces are facing upwards to do things like add dust or add moss or anything like that. And so if I use that same dot check and use my color visualization on this column, we can see I'm going to align this to 0, 1, 0. We can see any faces that are facing up towards this point are green. Any faces that are facing away from it are this red color. And so that could be great. You could even, this is how the angle of light rays would also be calculated. You could use this for some like stylistic shading. If I moved this point over here to the left, now you can see that maybe the sun, it's winter and the sun is low in the sky, and moss would be growing on this side of this column, and then on this side it's all red because all of those normals are facing away from this point. So you can almost think of that dot product like a light. This point is a light source, and then anything in the shadows is returning a negative dot product. Anything in the light getting hit or facing right towards those light is returning a positive value. So that's pretty interesting. And I could play around with this to get any sort of stylistic look I want. I could just turn it to black and white here. And now it almost looks like we are just having lighting information instead of shading. So if I move this over to the top, you can see it almost looks like a light source, which is pretty interesting. You could clamp this and make more of a harsh look. You could bring that into a material network. You could do tons of interesting things on a shading level with this. You could use it to push points in a certain direction. You could use it to detect if something is facing a certain way and trigger some other action in an interactive type environment. But that's really the basis of dot product, seeing if two things are aligned. And one practical application I like is shading geometry, using it almost as a mask for mixing materials. Another practical application would be scattering things on those areas that are facing a certain vector. So you could use that for something like moss, as I have here. Let me just color this to make it a little more clear. So we have this rock, and I could use the same sort of setup here where I have a point, and I could move this around and we can see the moss is only growing on the faces of the rock that are aligned towards that circle. So you can see I can move this all around. Now it's growing underneath. So it could be pretty handy to make masks for scattering things as well. And you can always adjust how clamped those values are and get some interesting results here. All right, so that's the basic of the dot product. Now let's look at cross product. So this is a little bit of a different animal. Let me jump over to here. What the cross product does is given two vectors. So if we see here, we have y and z. So you can think of these as 0, 1, 0 as the actual vector, and 0, 0, 1 for y and z. If you have two vectors and you need to know the perpendicular vector, that is where cross product comes in handy. So the dot product returns a float value or singular value from -1 to 1. The cross product returns another direction or another vector that is perpendicular to two vectors that you give it. So in this case, if we have the vectors of y and z and we ran a cross product on it, we would get x. So if you take these two directions and you think of it almost like a face, a polygon that it draws, you're almost calculating the normal for that face when you run a cross product operation on those two vectors. And I just give an example of that just so we can see the actual code. We have the first vector there is y, so 0, 1, 0. The second vector was 0, 0, 1. So those are those two arrows here. And if we use the cross function, so the syntax for that is cross, and then you feed in the two vectors, which is dir1 and dir2 in my case. If we look at the result of that in the geometry spreadsheet, you can see that does indeed return 1, 0, 0, or x, the x-axis. So that is cross product. It returns the perpendicular direction. Okay, so this is kind of a weird noodle graph, but I'm hoping it showcases exactly what's happening under the hood, because sometimes I think this cross product might be a little tricky to visualize when you're dealing with it. One really great application of this cross product is controlling the directionality or flow of like hairs for a hair system. If you start off with something like a sphere here, and we give it normals, so the normals just face straight out perpendicularly to those points, we can calculate the cross product to get a flow of vectors that adhere to the face or the directionality of this mesh. So let's take a look at this. Don't worry too much about exactly what these nodes are doing. As I've said, this is really just creating a visualization here. So what we're seeing here, let me disconnect this, is the blue lines are representing the normal vectors. So all those are facing straight out. That makes sense. Let's say we run the cross product operation here. So here's the cross with another vector, in this case, y. So that is straight up on all points, and that's represented by this green vector. So y is facing straight up, blue is the normal. And we're going to run the cross product operation on every single one of these points to get the vector that is perpendicular to these two axes. So where would you think this would face? If you're looking at these lines, if you had to take a guess, where would that third vector direction face? Well, let's take a look. Let's see. So I'm going to plug in that third vector that's pre-computed, and there we go. So if you thought it faced this sort of yellow swirling direction, you'd be right. So this is a little confusing, but let's kind of zoom in on some of these axes. You can see, imagine this green and blue line here form almost a triangle if you connect these 2 points at the top, or a quad. You could imagine a quad. This yellow axis is now facing perpendicular to that triangle. And you can see it doesn't have to be a perfect square like in my first example. These axes can be, or vectors can be very close together, but that yellow cross product vector will always face perpendicularly. And if we just preview that by itself, you can see it's almost this swirling around the sphere. So that's kind of interesting, but not too useful in terms of hair. Maybe you want the hair to face a certain direction. So this is where we can do a double cross product. So if we take this first cross product and cross it again, we will form another sort of flowing vector. So let me plug in this double cross product and see what we get. So this is the pink line, and you can see all of these pink lines are sort of draped downward and flowed down the sphere. And so just to sort of look at this, let's take away the up vector, which we're not using anymore. We're crossing the yellow vector and the blue vector, and that's making this purple or pink vector that faces downward. So you can see all the pink lines are perpendicular to the blue and yellow face that these make. Okay, so let's look at a practical use case of this. And one is to start an initial groom for something like hair. So if you had something like a sphere, and let's create some normals, and those will face all the way out. If we were to just do something like take a line and copy that to all the points on the sphere. Let's make this line face outward. We would get something like this. So really like spiky hair style, or maybe this could be like a dandelion or something like this, where we're having all the hairs face exactly in the same direction as the normals. But maybe you want that hair to flow over the surface like we were doing in that other example. So let's take this sphere and just clip it in half and scatter a bunch of points on top of it. And let's utilize our double cross product trick here and scatter some lines again. And now we get this sort of effect where these lines are almost getting blown away from this point. So if I move this point, so this is the reference vector that I'm using. Instead of just straight up, I'm using this position in space as my first cross product. We can see it's almost creating this sort of flow where all the hairs start orienting away from this point in space. So that's pretty nice, and they're flowing around the sphere. If I preview this with this hemisphere, so that could be really great to start a groom just to get an overall directionality. You could animate this to get some more motion graphic effects. Here I built in a slider where I can mix it with the normal N, so we can go from just using the straight out normal to scatter the hairs, and then we can kind of almost wet them and have them droop down using that cross product. We can of course do things like bend those hairs and do different things like that. This, if we up the length, we might start creating something that resembles more like of an organic flower, which could be an interesting technique to use. And yeah, That's cross product. So that is pretty handy, pretty useful. I find myself reaching for the dot product, I think, more than the cross product, but I've seen this used creatively in other ways. I think in an Intagma tutorial, they were using it to model raindrops, so you get the correct stretching of that geometry based on the cross product or the direction. Very, very useful. And that's where I just smashed together that dot product example and the cross product example to just get this interesting abstract kind of trunk and feathery hair thing on top. So yeah, that's the basics of cross product and dot product. Remember, the dot product will return a float, so a single value. The cross product will return a vector or 3 values. Dot product is used to see if things align in direction, and cross product is used to get that third perpendicular axis. So a lot of times you'll see this hand trick where Y is your thumb, X is your pointer finger, and then if you put your middle finger out, that's the Z. So I'm trying to see my webcam here. So X, Y, Z, there's my cross product. My middle finger is my cross product. Not sure if that helps. Anyway, love to see if you come up with any cool creative visuals using these techniques. Let me know if you have any questions in the comments, and have a great day.